So, welcome to the first technical session of International Conference on Futuristic Materials. Now, I would like to invite Chairman of this technical session, Professor Lallan Yadav from Department of Physics, Gorakhpur University, and co-chairman of the session, Dr. Nikhil Kam Shukla from Department of Chemistry, DDU Gorakhpur University. Please, sir. Now, I would request Professor Lallan Yadav, sir, to conduct the session.
Thank you, Dr. Amrish, giving me opportunity to chair this technical session. First, welcome to all in International Conference on Futuristic Materials 20. Now we are going to start our technical session first. In this technical session, we have 4 lectures, 3 invited talk, and 1 plenary talk. Plenary talk will be delivered by Professor Shyam S. Pandey on the topic of playing with molecular orientation in conducting polymers and their 2D positional mapping for high performance organic electronic devices. Before I invite to Professor Pandey to deliver his talk, plenary talk, I would like to introduce to Professor Pandey. I am very happy that Professor S.S. Pandey belongs to district Kushinagar of Uttar Pradesh. He graduate and post-graduated in MS Chemistry from Gorakhpur University, Gorakhpur. Professor Pandey, after that, he obtained his PhD degree from National Physical Laboratory, New Delhi in 1977. In the area of synthesis, characterization, and application of organic conjugated polymers. After that, he joined as a PDF in 1998 in Japan. He worked as Fukuoka Industry, Science and Technology sponsored postdoctoral fellow in Kyushu Institute of Technology from 1998 to 2001 in the area of photofunctional materials and devices. He was JSPS fellow from 2001 to 2003 and Knowledge Clusters invited researchers from 2003 to 2007. I am happy to know that he has received National Technology Award from National Research Development Corporation, Government of India in 2005 for development of glucose biosensor. So his contribution in the area of the biosensors is very promising because on the basis of his research, which has been carried out, converted into the device form. That is very good. Now, this glucose sensor is currently manufactured and marketed by Pulusatmu Healthcare Limited. So this is one of the scientific contribution of Professor Shyam S. Pandey. Also, he worked in QC Institute of Technology as assistant professor from 2009 to 2012 in the area of design and development of novel photofunctional materials for their application in the area of next generation solar cells. Currently, Professor Pandey is an associate professor of Graduate School of Life Science and System Engineering QC Institute of Technology since 2012. He has published more than 200 research papers in a reputed international and national journals. Also, he has published more than 470 papers in domestic international conferences and about 30 patents in India, Japan, Europe, and US. His research interest areas lies particularly dye-synthesized and organic solar cells, quantum chemical calculations, organic electronics and optoelectronics, organic conducting polymers, biosensors, and protein biochips. So after introducing Professor Pandey, I would like to invite him to deliver his plenary talk on the topic playing with molecular orientation in conducting polymers and their 2D positional mapping for high performance organic electronic devices. Professor Pandey.
Okay. So, am I audible?
Yes, sir. Yes, sir.
Yes,
Okay.
sir.
Okay, thank you. So, thank you very much, Professor Yadav, for a kind introduction. And before starting, let me share my presentation, and then I can talk. I believe it should go in PowerPoint mode. Okay, done. So first of all, I would like to thank the organizer, and especially thanks to Professor S.N. Tiwari, and whom I know very well. And a few months ago, I was having international webinar in chemistry department. He was also attending there. And at that time, he told me that be ready for some time. And that day came today. I am very happy and privileged to talk in my own university, where I used to play, go here and there and study. It is really nostalgic feeling. So well, as the topic has already been introduced by Professor Yadav, that few keywords like conjugated conducting polymers, orientation control and mapping, and their application in organic electronic devices. So I'm going to talk on these topics. Before starting the actual topic, just about a brief introduction. As I'm located in Japan, as you can see, it is in the center of the globe. And in Japan, as Q-Tech mentioned, south part, Japan has 4 major islands. So one of the big island, although more than 2,000 islands are there, small and big. So this quite big island, Kyushu Island, and the north part of Kyushu is Kita-Kyushu. In Japanese language, Kita means north. Is our place and city. Our institute, we have 3 campuses. As mentioned, I'm currently in Wakamatsu campus, which is one of the newest campus. It started from 2001. This is located in a map you can see in Science and Research Park by red dotted circle is our institute. It is only graduate school. So only MTech and PhD are there with limited number. Maximum capacity, 138 students, masters, and 38 PhDs. We cannot take more than that. Other 2 campuses are big. They have UG, PG, and all that. And around 70 professors. So ratio is nearly 2:1. And so in our Science and Research Park, we have 4 graduate schools, 16 research institutes, 54 companies, exchange and collaboration, and common educational research principle. Means from any of these universities, students can take the classes to complete their credits from any of the university. So this is common curriculum. Just about my group, my lab is Organic Photofunctional Materials and Device Lab. Main research theme is 3: next generation solar cells, organic electronic devices, bioimage sensors. So 3 major areas, not going to much detail. So just a brief that what we do. And especially today's topic is related to organic electronic devices. So this is one of the major thrust area in my lab, where what we do, we develop novel organic semiconductors, we design and simulate the organic semiconductors, we develop technology and method and optimize for the thin film fabrication and characterization, and making organic electronic device elements and their characterizations. So now moving to our main topic, that many of you might be sometime having a question. And anyway, before going through, I would just like to make a pardon. That time is very less, only allotted 30 minutes. It is very difficult for me to just justify in 30 minutes, but try to. But if I exceed 5-10 minutes, please pardon me. So very obvious question might be there, that, well, why world is interested in organic electronics, including our group as well. So first I'd like to say that everybody is knowing, and basically the physics background. So Gordon Moore, who is the co-founder of the Intel, he proposed the famous Moore's law. And he said that transistor and microchip will double every 2 years. That continued until 90s. And the processors are basically the elements are memory or logic element is transistors. So we can say transistors are shrinking day by day. But if we talk on economic aspect, when shrinking, basically using deep UV lithography to make smaller and smaller devices, and initial cost to establish a foundry for making 28 nanometer gate cost 30 million. Going to more lower down, 40 nanometer chip, $80 million US dollar. And if we want to make a foundry at 7 nanometer, it costs $271 million, quite costly affair. Now there a debate is also going on, whether do we need to make more smaller? And from physics point of view, limit is going to come because we cannot reduce the gate length because of electron tunneling problem, less than 5 nanometer. Okay. It means in downsizing, we are nearly going to reach near the threshold. With that, what we have achieved so far? We developed supercomputer, which normally works in a common von Neumann architecture, where the CPU unit and memory unit, they are separated and interlinked. This is quite different if we compare with the brain. The beauty is, brains don't need silicon. It has organic molecules and polymer. And the beauty is very anisotropic information transfer. There is no crosstalk. the information of touch, sight, smell, feeling, moving parallel on micron distances, but still there is no crosstalk. Such things physicists know go with perfect crystals and with a very high speed data processing. This is a famous supercomputer, K computer developed by Fujitsu. It is considered to be compatible data processing like a human brain. But how about the power? K computer uses 20 megawatt power to run, costing around 20 million Japanese yen per month, nearly 2 crore yen per month electricity bill. How about the human? It takes 20 watt, in background 90 watt. Much more, million times energy efficient. What does it suggest? As a future electronics, what we need, it is needed brain-like processing, means fast processing with low power consumption. So we have to learn from the brain. And in that case, neuromorphic device is a prerequisite. In neuromorphic computing, this is based on analogy of the neurons of our brain, which are made of synapses, because with synapse, two neurons are connected and data is being transferred. Just to give a brief example, there is a famous IBM's Blue Gene L supercomputer. They tried to simulate the mouse cortex in a collaboration with IBM Almadine Research Group and University of Nevada. They used 4,096 processors, each with 256 MB memory. They simulated half of the mouse brain using 8 million neurons with 6,300 synapses. Computer run only for 10 seconds with a speed of 1/10 of the real mouse brain. Means supercomputer is even slower in decision making and efficiency as compared to even a rat. Forget about human being. So brain-inspired organic electronic devices have a great future. Now to give you some glimpse of the wonder world of organic electronics, it is not very old, less than 40 to 50 years old. But we are now having electronic circuits based on organic semiconductor and device elements. We have demonstrated flexible e-paper, flexible solar cells, which can be produced in roll-to-roll fashion. Organic light emitting diodes. Now 80-inch TV is available by Samsung in the market based on OLED, which is a wide viewing angle, clear contrast. So organic electronics has traveled quite far and is still a huge potentiality. This field of organic electronics is emerging, growing more and more. And basically, if we go at the bottom, it uses organic semiconductors. And amongst organic semiconductors, organic conducting polymers, their role and contribution in organic electronics cannot be denied. They are quasi one-dimensional macromolecules. They are solution processable. And many applications in flexible displays, organic thin film memories, smart card, RFID card, and e-paper has already been demonstrated. We know that the backbone of various electronic devices are organic field effect transistors, working as a switch, logic gate, amplifiers, and different circuit elements. In a typical, although many device architecture exist for OFETs, in a typical bottom gate top contact device architectures of OFET, we know that thick film is not necessary. Few nanometer thick semiconductor layer on gate insulator is enough. So the cost depends on how we make a thin film. And quality, performance depends on what is the quality and nature of these organic semiconductors. As I told that organic conducting polymers are the planar one-dimensional macromolecules. So they have a very high inherent tendency of molecular self-aggregation. And this molecular ordering controls the device performance. For example, I will take a typical poly-3-hexylthiophene. Now this is organic semiconductor, polymeric semiconductor, commercially available by Eldridge Company. And it has been demonstrated that increasing the molecular weight, as you can see in this slide, increases the charge carrier mobility. And since we know they are quasi one-dimensional polymers, so the charge transport is basically first fastest intra-chain, followed by inter-chain hopping, and by self-aggregation, they make a domain, then inter-domain hopping. And this controls the overall charge transport. So what is needed? We need a large domains. And if we talk about electronics, especially the field effect transistors, if we can align the domains in the direction of source and drain, no doubt we can enhance the performance. So, take-home message is, we need large area thin film processing with pronounced carrier transport for efficient devices. As we all know, spin coating is still at lab level most preferred technique to make a thin film. Later on, many techniques, as mentioned, to promote self-assembly were developed. And further, to promote molecular alignment of these macromolecules, many techniques have also been reported. Amongst, I highlighted the friction transfer. This is another solventless technique. Our group has done quite a bit of work, and we improvised this method also. But I will not go into detail of this method. But we have pretty good work using this method. Amongst these methods, what I have told, that if we have to make a multi-layer, especially for thicker films, They suffer in triggering issues like mechanical damage, compositional damage, and solubility issues. To solve this issue, our group has developed a novel method inspired by Langmuir-Blajet technique. This we called FTM, floating film transfer method. This method is very simple. Any lab, anywhere can be done, and now this method has become worldwide quite popular. For example, we take a petri dish with some solvent, say for example, alcohols or ethylene glycol. So this works like a liquid substrate. Onto this, we put a drop of semiconductor solution, say for example, soluble in chloroform. So these two solvent doesn't mix. And when we put a drop, it spreads. And when solvent evaporates, a solid film floats onto the liquid substrate. And this can be transferred easily. So the beauty of this method is isolation of film formation and casting. We transfer solid film. So there is no detrimental effect, mechanical, chemical, and compositional damage. Second, what happens actually when from solution state, as my cursor is moving, where the molecules are randomized, when they move, it flows, solvent goes up. By controlling the viscosity of the liquid substrate, which is opposing dragging force, it aligns the molecules. So it not only makes a thin film, but also it makes oriented or aligned thin films. Just because I have lack of time, I have shown the superiority of our method as compared to conventional spin coating method. Films are uniform, anisotropic, and oriented, which is not possible by spin coating. And cost at lab level even 25 times cheaper. Cost downing of organic semiconducting element. These beauties make this FTM or floating film transfer method more popular. Second, how to know at lab level films are oriented? We can use a very simple polarizer film and rotate 90 degrees. If we make a color difference, we can see they are oriented. We can use electronic absorption spectroscopy as shown here. We can see the same film upon moving parallel to perpendicular. There is a clear contrast in color, exhibiting orientation. Quantitatively, we can estimate by comparing the absorbance peak ratio after parallel and perpendicular rotation of the polarizer that we call optical anisotropy, DR or dichroic ratio. We can use polarized FTI or polarized Raman as well to characterize the oriented thin films. We have last year reported a quite big review article about the charge carrier transport in field effect transistors, especially implications of the orientation. As we know, the charge transport in these quasi one-dimensional conjugated polymers, highest in conjugation direction, then pi-pi stacking direction, and then side chain stacking directions. Take an example of the side chain and the main polymeric frame. Depending on the processing condition, they attain edge-on conformation. Like standing, Alkyl chains are out of plane, and pi-pi stacking in the same plane. Such molecular orientation is suitable for in-plane charge transport like field effect transistors. Another architecture they can attain, the face-on, where the alkyl chain and main pi stacking in the same plane. Such the molecular architecture is suitable for sandwich or vertical devices like diodes and solar cells. We used different type of conjugated polymers, as you can see here. They all have been oriented by our method. One of the beauty I wanted to show that this is polythiophene, one of the organic semiconductor commercially available. It comes in two versions, regio-regular and regio-random. Or non-regio controlled, we call NR. NR was discovered long back in 80s. Regio-regular is costly, less yield. But people are using because NR charge transport is hampered. Mobility in the order of 10 to the power minus 5 centimeter square per volt second. That's why people use regio-regular. We have demonstrated. This is my one of student who is now just joined this year assistant professor in another national institute in Japan. He graduated 3 years ago from my lab. He should see the spin coated film of the same material, NRP3HT, featureless. But when we prepared the thin film by our method, we can see very clear, not only the red shift, very clear bibaronic structures, suggesting enhanced intermolecular interaction and extended pi conjugation, along with the orientation, which is very similar to the regio-regular one. So even that material, after orientation, we can improve their characteristic. And that was reflected. See the spin-coated film, AFM picture. And when FTM, all the molecule assemblies, they are oriented in one direction. That we can now very easy, if we can coat the source and drain like here and here, the transport will be highly favored. We can found by in-plane and out-of-plane XRD that these molecules are not only crystalline, you can see here. The black one is spin-coated and the red one FTM processed. Very clear, even in polymeric system, we can see 100, 200, and 300P. So films are more crystalline and edge-on oriented. And that reflected when we make the field effect transistor. See, the spin-coated mobility 10 to the power minus 5 enhanced 2 orders of magnitude minus 3. So we can enhance the property. Another, this is recently developed after 2000, a liquid crystalline polymer. It has solubility issue and it needs to heat more than 160 degrees Celsius near its LC temperature to align the domains. We used our method. See, at even room temperature, the films are oriented. And when we heat anneal to remove the solvent, it becomes highly oriented. This polymer is so rigid that it is difficult to orient. But if you see the worldwide method reported by different groups in the world, we have got highest orientation with purely edge-on orientation that we published 2 years ago. XRD suggested, very clear, you can see the in-plane and out-of-plane XRD suggests it is perfectly edge-on oriented, which is highly suitable for in-plane charge transport.
Sir, Pandey sir.
Yes.
Since time is limited,
yes,
so
sir.
please conclude.
In how much minutes?
5 minutes.
Oh my God. Okay. So just let me give the glimpse. So this has resulted into the very high mobility, which is more than amorphous silicon and one of the best in the world. We can make a multi-layer coating for polarized emission or LEDs without disturbing the underlayer. Let me go. We improvise this method that we call ribbon Spectra floating film transfer, which can make a large area, 2 centimeter by 20 centimeter homogeneous film. We tested them. We can see this large area. The tray is 30 centimeter longer and 15 centimeter wide. You can see these films of different conjugated polymers. Now I will quit this. One story I will take that actually long back in thiophene, when we do increase the chain length, solubility increases, but mobility drastically decreases, especially in the longer chain. That I called fighting with devils. We made the large area film, proved edge-on structure, suggested interdigitated edge-on oriented molecular architecture. And the beauty is that even in the longest chain, mobility was not hampered. So mobility got independent. So why previous group, they found hampered mobility that was answered by molecular architecture, because spin coating gives phase and configuration. Carriers have to pass through the alkyl chain length, while in edge-on, it vanishes. So there was no effect. Finally, we developed a new system because transistor has a channel length only 20 micron. So in 1 millimeter, we can have more than 50 transistors. So we need to probe the orientation very finely, which is not possible by standard electronic absorption spectroscopy. This girl graduated last year from my lab. We developed a new system. It has computer-controlled XY stage, light source, and multi-channel photodiode array detector. So all the wavelength of light falls together and simultaneously detected within 10 milliseconds one spectra. The stage moves and we can see the mapping. We can map the orientation as well as the thickness. And result was very similar to the conventional spectrophotometer. This much data will take a day, which was finished just in few minutes. This is the mapping pattern of a large area film of thickness and orientation distribution. As you can see, in the top area, films are highly oriented with DR index of 30 to 40. And when we use this highly oriented films using this semiconducting polymer, this has also reported one of the highest reported mobility in the world. We use this method to map the orientation and thickness uniformity by thin films made by different methods, FTM, friction transfer, and spin coating. And we proved and demonstrated its versatility. Finally, I would like to conclude my talk on these conclusions, acknowledge present and past members of my lab and financial support for RCSG INRON, and you all for your kind attention. Thank you very much.
Thank you, Professor Pandey, for a very nice and informative lectures. You presented all the aspects regarding the topic of the lectures, prospectus and challenges with the thin film fabrications, particularly multi-layer thin film, which is fabricated using a new techniques, as you have described, floating film transfer method. That is very important and informative for us, those researchers who are working in the area of thin film. Another aspect of your lecture is the recent advances in the orientation of conjugated polymers. So we are very thankful, sir, for your nice lectures. Just one, I have a question, sir.
Sure.
Particularly, I am also working in the area of thin and thick film gas sensor.
Okay.
So for gas sensor, in order to improve the selectivity,
Yes.
how one can use the multi-layer structure? What is the role of multi-layer structure to improve the selectivity of the gas sensor?
Two things. Of course, selectivity depends on other factors as well. For example, what kind of, I don't know what kind of material you are using. So one is the material aspect and another is the thin film aspect. So the thing is that when we are going for multi-layer, because actually intrinsic property comes from our characteristic of the main component. So if in the multi-layer, if their nature is not being altered, it will maintain the selectivity in my opinion. But
Thank you, sir.
Yes, sir.
Thank you. Thank you very much, sir. Now, in this technical session first, next lecture is...
Okay, I will stop the share.
Okay, sir.
Okay.
Okay, sir. Thank you, sir. Dr. Bimal Kumar Tiwari, आवाज मेरी आ रही है? हेलो, मिश्रा एक कनेक्ट है कि नहीं? हेलो,
Dr. Tiwari, are you connected?
Dr. Tiwari, hello.
Ask him to unmute. Yes, yes.
Please unmute.
He is connected, sir. He is connected.
Okay, okay.
Yes. Dr. Tiwari, you can now share your screen.
Okay, thank you.
He is not audible.
My voice is coming or not?
Yes.
Hello.
Okay. Okay. Hello.
Yeah, hello.
There is some noise in your voice. Rest is okay.
Now it is okay.
Still.
Okay.
Hello.
Doctor. Hello. Now I invite. Hello. Hello.
Hello.
Dr. Tiwari, are you hearing me?
Yes, 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 sir. Voice is clear. Your voice is clear.
Okay. 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 Now I invite Dr. Tiwari to deliver invited talk on the title Development of Conducting Sulfur Nanocomposite Cathodes for High Performance Lithium Sulfur Batteries. Dr. Tiwari is MSc in Physics from Banaras Hindu University. He obtained PhD also from the same university in the School of Material Science and Technology, IIT BHU. Dr. Tiwari presently working as a pool scientist in the Department of Physics, Banaras Hindu University. He has published more than 18 international research papers in a very reputed journals. His Current research areas are electron irradiation on fluoropolymer and its nanocomposites, ferro and piezoelectric properties of fluoropolymers, synthesis of porous carbon nanospheres with high surface areas, LIS and sodium and battery applications. Now, I invite Dr. Bimal Tiwari to present his talk. Dr. Tiwari.
Thank you very much, Professor Lallan Yadav, sir. And there was a very nice talk by Professor S.S. Pandey, sir. So he explained all the things about the organic electronics devices and for transistor devices. So now my today presentation topic is development of conducting sulfur nanocomposite cathodes for high performance lithium sulfur battery. So my outline of today presentation is, first I will introduce about the battery, primary battery, secondary battery, then type of secondary battery, lithium ion battery, lithium sulfur battery, and sodium ion batteries. And then I will explain the research development on lithium sulfur battery. So here I will discuss my work. I prepared the cathode based on the sulfur copolymer and porous long carbon nanotube composite. Another work I did, I used the EDA assisted. I used the EDA to make the high conducting RGO, and I prepared the nanosulfur RGO composite cathode for high performance lithium sulfur battery. And then I will conclude my work. So as we know that the day by day energy consumption is increasing, and because of the population, economic growth, and we are using many devices, portable devices, movable devices, and we know that the fossil fuels is limited on, and at this time 80% of our energy need is fulfilled by the fossil fuels, but in few years it will finish, and we need the more alternative energy sources. So many researchers is working on the solar energy and wind energy, nuclear energy to make like a energy source. But as we know that the solar energy or wind energy, continuously we cannot produce the energy in night or if there is no wind. So we need the energy storage device to store the energy, and as our requirement in our like mobile, laptop or movable device, we can use this energy through energy storage devices. So there are mainly two types of energy storage devices. One is the battery and another is the supercapacitor. So here I will discuss about the batteries. So battery, as we know that inside the battery there is electrochemical reaction, and it produces the energy, and it store the energy and it produces the energy. So in right side there is a figure, and we know that the unit of the battery is a cell. So this is the figure of the cell. There is a cathode, in anode, and in between there is a electrolyte, salt electrolyte. So we can prepare electrolyte three types. There is a liquid electrolyte, gel electrolyte, or solid electrolytes. So for the liquid electrolytes, we need a separator, because cathode and anode both are conducting. So to isolate these both electrode, we need a separator, and through cathode to anode and anode to cathode, salt means ions moves. And in left hand side, we can see the ion electron motion in the cell. So through external side, there is a motion inside the battery. There is a motion of the ions from through the oxidation or reduction. So this is the construction of a cell, a unit of a cell. And if we combine two cell or more than two cell, it is called the battery. So there, if there are a more number of cells, two or more than two, so we say it is battery. And batteries, there are two types of battery. One is the primary and another is the secondary. So primary battery is non-rechargeable. In daily life, we use the primary battery in the remote, in the wireless mouse, keyboard, or in many places watches we use. So just one time we can use, and it is not rechargeable. And secondary battery is a rechargeable battery. So secondary battery we use as a lithium lead acid battery, and lithium ion battery we use in mobile and laptop. So these are the secondary battery. So there are few examples of secondary batteries and its comparison. So here is lead acid battery, nickel cadmium, nickel metal hydride, and the lithium ion batteries. So specific capacity, internal resistance, cell voltage, toxicity, it is here it is compared. And we see that for the lead acid battery, the specific capacity is 30 to 50 milliampere hour per gram. But for the lithium, it is from 150 to 200 or 250 milliampere per gram. So for the lithium ion battery, the specific capacity is very high compared to lead acid battery. So that's why in daily life, we are using the lithium ion batteries because it is lightweight and very high specific capacity. Another thing is the cell voltage of the lithium ion battery is more than 3 volts. And for the lead acid battery, it is only 2 volts. So this is one advantage. Toxicity is low for the lithium ion batteries because in the lead acid batteries, there is acid, so it's toxic. And coulombic efficiency of the lithium ion battery is very high with cyclability. So this is the how the charging and discharging occurs. So there is a model for the lithium ion battery. So during the charging, the lithium ion moves from the cathode to anode during the charging, and electron passes to external circuit. And anode is made of the graphite, whereas cathode is made of the lithium cobalt oxide. For sodium ion batteries, mechanism is same for charging. Just we use hard carbon in place of graphite, and NMC means sodium nickel manganese cobalt oxide we use as a cathode. There are many cathodes. So just this is as example for sodium ion battery. For lithium sulfur battery, we use the lithium metal as a anode, and sulfur we use as a cathode. But mechanism for charging is same for the lithium ion batteries, sodium ion batteries, and lithium sulfur battery. During the discharging, the lithium ion moves from anode to cathode. So we know in the anode, the lithium is in the form of lithium metal. So that's why in anode, lithium has a high electrochemical potential, whereas in cathode, lithium is in compound form in cathode, so it has low electrochemical potential. So that's why during discharging, easily lithium ion moves from anode to cathode. This is the mechanism, and same happened with the sodium ion battery, lithium sulfur battery. So now I'm focusing with lithium sulfur battery. So this is the in left hand side bottom, you can see the a cell for lithium sulfur battery. Lithium is made of the lithium, anode is made of the lithium metal, and cathode is made of the sulfur. And during the discharging, lithium ion moves from anode to cathode, and it reacts and finally form lithium sulfide. So at top you can see the S8 on cathode, and at bottom Li2S. This is the final product formed after the discharging, and in between there are intermediate species during the reaction. And we know that the lithium sulfur battery has 3 to 5 times higher specific capacity compared to lithium ion battery. For the portable devices or for lightweight, lithium ion battery is very successful. But for the heavy vehicles, for the aeroplanes or trucks or heavy vehicles, we need higher energy, and that's why we can implement the lithium sulfur battery to store the energy, or means to take the energy from the battery, stored battery. So for the heavy vehicles, lithium sulfur battery is very useful. But with lithium sulfur battery, there is a problem. And there are mainly three challenges we need to overcome. So one is the conducting network. So as I told that cathode is made of sulfur, but electron is coming from the external circuit, and this cathode should be conducting. Okay, and sulfur is anode. So we need to mix good conducting material where we can propagate the electron. Another is binding of sulfur. So we know that the sulfur binding is very poor. It will easily dissolve. So we need to search, or we are working how we can bind the sulfur together. And another is the maximum utilization of sulfur. So to get the maximum energy density during the discharging or charging, maximum sulfur should react. So the another challenge is cathode should be porous. So if it is porous, conducting and binding is good, then it will show good lithium sulfur performance, better performance. So this is my work where I try to overcome this limitation. So what we did, we used the solution technique to prepare this composite. First, we dissolve the sulfur in DMSO, and we co-polymerize with DEB monomer. So we added the DEB. So we prepared the sulfur polymer, and then we added the long CNT, is special type of CNT. So it is porous and highly conducting. It has very high conducting network. And then we mix at high temperature. Then we prepared the composite. So we did the TGA. From TGA, we get that the sulfur percentage is around 58% in the composite. So it's very high loading. And we did the XRD of this composite. So below in XRD, you can see the top one is the for pure sulfur, and bottom is the sulfur copolymer. So in sulfur copolymer, there is no pure sulfur, crystalline sulfur. So from XRD, we can say that there is complete polymerization of the sulfur. This is the SEM image of the long CNT and composite. So figure A, B, and C are the SEM image of the pure long CNT. So you can see that there is a very long chain of CNT network, and it's porous. Due to the interconnection, the conductivity is very high, and surface area and porosity is also very high. I mix the sulfur copolymer with this conducting CNT, and the figure D, E, and F, we can see the absorption of sulfur copolymer with this long CNT is very nice, homogeneous, and there is no isolated sulfur copolymer. So with this solution method, mixing is very good. But we did at very high temperature, above 150, because polymerization and mixing should be homogeneous.
Hello.
This is the EDX of the same material, and we can see that the image P is showing the carbon distribution, and image C is showing the distribution of sulfur. So you can see SEM image, there is a very nice distribution of sulfur inside the CT channel. So we can say from this figure, the sulfur dispersion is very good in the CNT network. And this is the battery performance of this composite. Figure A shows the charge discharge curve. It is very nice, ideal charge discharge curve. The polarization between the charge and discharge curve is very low. the capacity during first cycle is more than 1000, and still after
Dr.
100
Tiwari?
cycle.
Excuse me, Dr. Tiwari, please conclude within 5 minutes.
Okay. So after 100 cycle, we found that still we are getting more than 700. Specific capacity is around 700. So it's very good specific capacity. Figure B shows the cyclability of this composite, and up to 200 cycle we get very good specific capacity. So cyclability retention is very good. C is the CV of this composite. It is showing oxidation and reduction peak, and D is showing the rate performance at high current rate. It is showing good specific capacity. This is our another work where we mix with the RGO and nanosulfur we prepared, and we did the hydrothermal. We got the hydrogel of this composite, and it is also showing very good porous structure, conducting network. After hydrothermal, the conductivity of this composite is 1.83 Siemens per centimeter, and PM also support SCM results. We did lithium sulfur battery performance and CV, the charge and rate performance. It is showing very high specific capacity at low current as well as high current. And figure D is showing the cyclability of this composite. So we can see that after 100 cycle, the retention is very good. Only 20% loss of specific capacity we get. So this composite is showing high capacity after 100 or 200 cycles. So this is our summary. So we can say that for the heavy vehicles, we can use the lithium sulfur battery because 3 to 5 times it has higher specific energy compared to lithium sulfur battery, lithium ion battery. And in my work, I prepared the sulfur copolymer, which is homogeneously distributed and well binded with long CNT channel. Its capacity we get up to 1040, and around after 200 cycles we get 610. So it's still very high. And with Geo also we are getting very good high conducting network of this composite and nanosulfur. We are getting 1.83 Siemens per centimeter conductivity. Capacity is about more than 1400 at 0.1. So we know that the critical capacity of sulfur is 1672. So it's nearby this theoretical value. And after 100 cycle, we get the 741 capacity with very good Coulombic efficiency.
Thank you.
So these are the list of publications.
Okay. Thank you, Dr. Tiwari. You have presented your research work, particularly how to improve the performance of lithium sulfur batteries using conducting sulfur nanocomposite cathodes. Thank you for your presentations. Thank you.
Thank you.
Yes, sir. Please proceed. Professor
Our
Lallan
next
Yadav, sir.
speaker. Hello.
Yes, sir. Please.
Dr. Rohit Sahi. Now our next speaker is Dr. Rohit Sahi from Gaya, Bihar. Is available?
Yes, sir.
Is he available here?
Yes, sir. Yes, sir.
Okay. Dr. Sahi,
Yes,
are
sir.
you hearing me?
Yes, sir.
Are you hearing me?
Yes, sir.
Okay. Now invite Dr. Rohit Sahib for second invited talk on the title Magnetic Properties of High Entropy Alloys. Before that, briefly, I would like to introduce Professor Sahi. Presently, he is working as assistant professor in the School of Physical and Chemical Sciences of Central University of South Bihar. Before that, he also worked as assistant professor under Inspire Faculty Program in MNIT Allahabad. Dr. Sahi research areas are magnetic and mechanical properties of nanocrystalline novel alloys, synthesis and characterization of novel hydrogen storage materials and quasi-crystal. Dr. Sahi has published more than 30 research papers in various international and national journals. He has written one book which is published by international publishers. Dr. Sahi also handled the research project amount of total 50 lakhs, and he has guided one PhD students. So now I request Dr. Sahi, please deliver your lecture. Dr. Sahi.
Thank you, sir. Am I audible?
Okay, okay.
Yeah. Thank you, sir, for a nice introduction. First of all, I would like to thanks to organizer for giving me opportunity to discuss my work at this place. So today I am going to deliver my talk on high entropy alloy for high magnetization and low corrosivity. These are, first we talk about what are the high entropy alloy, because these are some new type of alloy. So we all familiar about the conventional alloy system in which there is a one or two principal element. Sometimes we take more than two, but there is a possibility that if we increase the number of element, there is a possibility for the phase segregation and complex phase formation is going to take place. But in 2004, it has been reported by that JWN that they are going to make alloy by using more than 3 element. They try to make alloy by using a 5 element, and they try to make it. And they found that if we take these 5 elements, with the combination of these 5 elements, there is a possibility of formation of simple solid solution, even though there is a large number of elements, but there is a possibility of solid solution phase if these elements satisfy certain criteria. So if they define these alloy can be named as high entropy alloy because the configurational entropy of the system is high. They take we can define these alloy if the composition of the alloy lies between 5 to 35 atomic percent. Then we can say the configurational I just given the data in this table. If we are going to calculate the configurational entropy for different element, as we can see, as the number of element is going to increase, the configurational entropy is going to increase. And based on this configurational entropy, we can classify alloys in 3 different forms. That is if configurational entropy is less than R is gas constant. In that case, the alloys are our traditional alloy lie in this category. Another is that is medium entropy alloy, and for if the configurational entropy is going to greater than or equal to 1.5 R, in that case the high entropy alloys are going to form. So the basic idea of the importance of these alloy are that they have these 4 different characteristics. We can say there is a high entropy effect, severe lattice distortion effect, and sluggish diffusion effect, as well as there is a cocktail effect. Cocktail effect is nothing but that is a mixed effect. Due to the presence of large number of elements, the resultant property is going to change. So due to these 4 core effects, these alloys having some potential application in the aerospace industry, and as well as they can replace all the whatever existing alloys, conventional alloy in our traditionally existing they can replace all the traditionally existing alloys. So what are these effects? If we talk about high entropy alloy, we can say we are going to make alloy by using more than 5 elements. You just see this curve. If we are going to see this curve, we can see as we are going to increase the number of elements, the configuration entropy is going to increase. As the configuration entropy is going to increase, till we are using we can make alloy by using 13 elements. from 5 to 13, we can see the configuration entropy is going to increase, and after 13, the saturation is going to achieve. There is a slight increase in the entropy. And what is the benefit of the increase of this entropy? If by Gibbs free energy, if the entropy of a system is going to increase by this formula, we can see the system is going to, the Gibbs energy is going to minimize, and there is a probability of formation of simple solid solution phase. We can consider it by seeing this, by considering this example. As we can say, there is a formation of intermetallic phases are going to take place, and we are going to increase the number of element. As we are going to increase the number of element, you can say simple solid, you can see there is a possibility of formation of simple solid solution phases are going to occur. And we know that the mechanical property, magnetic property, and several other property of a material is going to depend upon which type of phases are there, as well as what are the microstructure of that material. So the second is there is a sluggish diffusion effect. We know that for normal alloy system, all the atoms are surrounded by a similar type of atoms. However, for the case of this high entropy alloy, the one atom is surrounded by 4 or 5 different type of element. So the diffusion of one atom to the other is very slow. Due to that, there is a possibility of formation of nano size precipitation is going to occur, as well as the lattice is also distorted. This distorted lattice is going to help to improve the mechanical property of a system. I have already discussed about that cocktail effect. So before the start for the synthesis, we are going to calculate some we go for the evaluation of some thermodynamical parameter, and based on these thermodynamical parameter, we can predict there is a possibility if we are going to select certain element, these elements are going to make solid solution phase or not. So these are the some criteria. We can see that if the configurational entropy lies between this to this, in that case there is a formation of solid solution phase is going to occur. So before start, we can predict the selected system, there is a possibility of formation of solid solution phase or not. So we go through this, and these are the some research trends. These are the list of these are the number of publication day by day, how the number of publications are going to increase in this area. So that is due to the importance of due to that property of these alloy. Different research group are studying these much you can say more focus on these system. As well as we can synthesize these alloy by using a traditional, whatever is the traditional synthesis routes are available, we can also synthesize these alloy by using traditional route system. But we synthesize this system by using a mechanical alloying technique. Why mechanical alloying? This technique is beneficial because sometimes some alloy having a slower diffusion, some elements having slow diffusion. So if we continuous milling is running for 10 to more than 20 hours, in that case the slow diffuse those elements having slow diffusibility, they can also diffuse properly. And we all know what is a basic that is a phenomena behind this milling. There is a constant welding and crack is going to occur. Due to that, a local heat is generated, and due to that, alloying is occur. So since these are a totally new system, we don't have XRD data for literature and all these. So we analyze these phases by using the Leval fitting, and that one is going to done by that Zana 2006 software. We just by observing the XRD peak, we predict that the phase is FCC, BCC, and based on that we give some structural model, and then we try to fit, and we will find what is the exact fit by this fitting refinement. And then we the crystallite size lattice strain is going to be evaluated by using this word function analysis. And these are the different instrument which are used for the which already used for the analyzing of these material. So today I am going to discuss some work which we did in last 2, 3 or 4 years. So these are the list of work which one is done by my PhD scholar. These are the list of publication, and just I want to give some glimpse about the what type of work we did. So we try to improve. We are going to study what is the addition of. We try to synthesize a high entropy alloy by considering a 5 element, that is a CRFE NiTi 4 element, and then we are going to add another additional element. This additional element is maybe we are going to select that aluminium, magnesium, and cobalt. by the evaluation of thermodynamical parameter, and we found if this combination, there is a possibility for the formation of solid solution phase with this combination. And then these are the data, and based on that we can predict there is a possibility of formation of solid solution phase. We go for the XRD. You can see there is this one is a hand mix sample. After 10 hours there is a formation of some new peaks are going to generate, and then again after 20 hours the complete the elemental peak is completely disappear and new phases are going to form. As well as after annealing, you can see that the only these the crystallinity of the synthesized phases is increased for the case of, that is, TIFE-NI CrCO. This one is the XRD data for the TIFE-NI CrMn. In the first case, there is a formation of only single BCC phase is going to occur. For the case of second case, there is a FCC and two FCC phase and one intermetallic sigma phase. Minor amount of that sigma phase is going to occur. And for the case of this AL addition, there is a formation of BCC and FCC. Both the phases are going to occur. This is a SEM analysis, and these are the you can say the crystallite size, lattice strain, the XRD analysis of XRD data, and these are the magnetic characteristic. You can see by the variation of only single element, there is a large change in the magnetization as well as the SC. So we can find it by this the synthesized having 24, the cobalt having 24, and Mn having 13, and this Al having 5.07 ms, as well as the SC is also, that is 150, and 84 is there. And also after the annealing, there is a change in these data, and this one is occurred due to the change in the lattice parameter, as well as there is a change in the we can see this by the XRD. There is a change in the ratio of the, after annealing, the BCC FCC ratio volume fraction is going to change, and we know that how when the phases are volume fraction of the phases are going to change, there is a change in the property relatively. Our this one is after that we found that already this CO FE TI system having some promising results. So we tried to improve the magnetization as well as corrosivity of this system by the variation of stoichiometric ratio, by the proper adjustment of stoichiometric ratio. And you can see this one is XRD data for the hand mist sample, and then after 10 hours the phases are going to form, and after 20 hours you can say all there is no any additional peak for the elemental peak is present, and then after 20 hours the complete transformation is going to occur, and with that indexing you can say there is a formation of two phases, that is a BCC FCC, and some small amount of that is you can say this is just like type impurity type phases, and this may form due to the presence of TI and NI. We can tune the formation of this TI and I R type phase by considering the by tuning the composition of TI and NI. So this one is a fitting of that data, XRD data, and this shows the you can say that there is the corrosivity of this material is going to the 15 hour state. So we can consider these material approximately we can say this material can be act as a soft magnetic material, because less than 12 is the soft magnetic material, but this one is approaches around the soft magnetic. We can say this can be used as a soft magnetic material by proper some tuning. And then the MS of this material is around 46 oersted. Sorry, for 46 EMU per gram. That is after this we go for that annealing. Our aim is to densify the sample, because the alloy is synthesized by mechanical alloying technique. So we have powder like sample. So in order to practical application, we must have densify our sample. For densification we go for the annealing, and our aim is, because the corrosivity is affected by the grain size, so our aim is to restrict the grain size, because if the grain size is going to large, in that case the material is going to be the corrosivity is going to be large, and the property of a material, magnetic property of a material is going to change from soft to hard magnetic material. So you can see this data. We anneal our sample for at low temperature 200 degrees centigrade and large duration, because we try to remove the strain of the sample, so that the magnetocrystallinity is going to increase. And based on that, after that annealing, you can see the crystallite size is going to be 10.81. That one is similar to the previous one, as well as we can see the change in this the data, that is magnetization MS and SC, is also going to be that is 81. The magnetization is going to be just double, but the SC is going to be 15, the same as that previous one. So we can somehow restrict the grain size. We are going to restrict that enhancement of the grain size by low temperature annealing, and this data shows that this is that your empty. Yes, yes, sir. Just 2 minutes, sir.
Okay, okay.
Okay. So this one is a empty, and from this you can see all these this material having the TC is more than 400 Kelvin. So this is the TEM graph, and you can say we also know that the corrosivity and all in magnetization, corrosivity is basically depends upon the particle size. So we can further confirm this. After the annealing, the corrosivity is going to be same, but the crystallinity of the material, the enhancement in the magnetization is going to occur due to the crystallinity, improvement in the crystallinity. And by SEM, you can say the morphology is also going to be same. All these enhancement in the material is going to occur due to the improvement in the crystallinity, as well as due to the densification of improvement in the crystallinity. So this one is a data we can say that for these material, by the variation of the single element, we can tune the property systematically. We can tune the property, and we synthesize material based on our requirement. And the basic thing is that the commercial soft magnetic material is the problem with this is that they are these material are the mechanical property of these material is not good enough. So due to that, and as well as the resistivity of these material, the conductivity of these material. So by using these high entropy alloy, we can synthesize a high resistive material, as well as the better these material can have good good magnetic as well as mechanical property. Combination of both the property, it provide a freedom to you can say this material can become beneficial for the industrial application. So next is acknowledgement. So I would like to thanks my collaborator and my mentor. So these are the financial assistant. I received financial assistant from this DST and SERB. These are the different institute through which I did my characterization of the sample. And this is this one is my PhD student, Dr. Rajesh Kumar Mishra. He recently completed his PhD on the same topic. And thank you.
Thank you, Dr. Sahi, for giving a very nice lecture. You presented your research work related to the high entropy alloys and their magnetic and structural properties. So thank you for this nice lecture. Now, in this technical session, the next invited talk is delivered by Dr. A. Reddy Palu, MREC, Hyderabad. So, okay, Dr. Sai. Next, we go to the next lectures.
Okay, thank you, sir.
Thank you.
Yeah, good evening, all. Hello, sir.
Okay. Are you hearing me?
Yeah, I'm getting your voice, sir.
Dr. Reddy?
Yeah, I'm getting, sir. I'm hearing.
Okay. So now I invite the last talk of this session, technical first, Dr. A.R. Reddy Palu, MREC, Hyderabad. And the topic of talk is novel nanocomposite polymers, electrolytes for rechargeable lithium-ion batteries. Dr. Anji Reddy Palu has completed his PhD at the age of 28 years from Dr. H.S. Gaur Central University, and he did his postdoctoral from Sogang University, South Korea. Dr. Reddy currently working as head of the Department of Physics, MREC, a premier engineering college in the Hyderabad. Previously, Dr. Reddy worked in VIT University and KL University as assistant professor. He has published more than 50 papers in reputed journals and has been serving as an reviewer for many reputed international journals. He has given many invited talks and keynote speeches in various countries in different international conferences. Also, he received many awards and honors for his contribution in research on energy storage, devices, and academics. Dr. Reddy, having 3 patents for his credit, his H index is of 21, which just reflects his research capability, and having more than 1200 citations. So with this background, now I request Dr. Reddy, please deliver your talk.
Yeah, thank you very much. Yeah, thank you very much, sir. Yeah, thank you very much, sir. Okay, first of all, I would like to thank organizers for giving this opportunity. And today I am going to deliver a topic on novel nanocomposite polymer electrolytes for rechargeable lithium-based batteries. Okay, this work I am doing from last 7 years, and whatever I did from last 7 years, I am going to present now. Okay, and already previous talks, Dr. Tiwari has given introduction to batteries, and here I'm not going to much focus on that introduction to batteries. Already in previous lectures they have given. Okay, yeah, this is the outline of my topic. I would like to give basic information about the lithium ion and lithium air battery, and in previous lectures Dr. Tiwari has given introduction about the lithium sulfur batteries. Okay, and what are the existing issues in these batteries, and what is the solution for those issues. Okay, and I will give small literature review, and after that I will present my results based on nanocomposite polymer electrolytes. Okay, and first one, why we have to go for batteries. Okay, everyone know about this answer for this question. The goal is to replace fossil fuels as our main energy source. Okay, everyone know about this fact. Okay, and where we use this energy storage devices. Okay, in everywhere maximum cases we are going to use these energy storage devices. And this primary battery, second battery, everyone know about this. Primary battery means only one time usable, use and throw, and secondary batteries, those are rechargeable batteries. Okay, where we are using, I have given here, applications also I have shown here. Yeah, this is the history of the battery. Okay, this is the complete history of the battery, and lithium batteries have started in 1990s, and the lithium oxygen batteries that have started in 2008. Okay, current energy outlook. Actually, nowadays we are looking for high energy density and high power density energy power sources. Okay, for that main alternative is lithium ion technologies. Okay, that is the main alternative source for any energy storage devices. That means particularly in electric vehicles. The energy density of lithium ion batteries is limited by the intercalation of chemistry of the electrodes. Okay, actually now at present we are using the lithium ion batteries, but there are also some limitations are there. Okay, how can we rectify those limitations? What is the alternative for that lithium ion battery? Here I have given the some data about all the batteries, and here the values they have given for theoretical specific energy and practical specific energy. We can observe these tables and diagram. Out of all the batteries, lithium air battery having the more practical specific energy or theoretical specific energy out of all the batteries. Okay, at present this lithium air battery is in research stage only, that is not at commercialized. Okay, at present only lithium ion batteries are commercialized what we are using. And the next, metal air battery concept. Why we have to use this metal air battery concept? Okay, that may be lithium air or zinc air or magnesium air batteries. Why we have to use this metal air battery concept? Because of high specific energy density is the result of the coupling of a reactive metal anode to an air electrode, thus providing a battery with an inexhaustible cathode reactor. Okay. And what is the advantage of this lithium air battery? Okay. Here I have given some advantages of that lithium air battery, that is having extremely high specific capacity of lithium anode material for lithium. Okay. And the couple voltage of lithium oxide in alkaline electrolytes, there is around 2.91 volts. And that lithium air battery, when fully developed, could have practical specific energies of 1000 to 3000. This is almost very high value compared with the lithium ion batteries or lithium sulfur batteries also. That lithium air cell is electrically rechargeable, far more so than zinc air battery. And this is the simple structures of lithium ion battery and lithium air battery. I'm going to compare these two only at present. I'm not going for lithium sulfur batteries. Okay. In case of lithium ion battery, we are using lithium based cathode materials, and lithium air battery, the cathode is oxygen, that is replaced by oxygen, remaining everything is same, anode, electrolyte, everything is same, but only one cathode material we are changing. In place of this lithium based cathode materials, we are going to change by oxygen. And this is the market of from 2015 to 2024, that is lithium ion battery market, first one, and the second one is lithium air battery market. Okay, but second one, that is in research stage only at present. Up to 2024 I have given here, until 2022 I have given here. And these are the different applications of lithium batteries. Okay, these are different applications of lithium batteries. And what are the gravimetric energy densities of different batteries I have given here. And out of all, you can observe the lithium oxygen, that is having more compared with the all. We can observe theoretical value and practical value. Green one is the theoretical and blue one is the practical. You can observe, okay, out of all, lithium oxygen battery having the more gravimetric energy density value. And I have given the applications of that lithium ion batteries in different applications, particularly in up to, by 2025, you can observe the graph. Okay, maximum percentage of electric vehicles occupied by this lithium ion battery only by 2025, maximum, that is by this lithium ion batteries in all maximum electric vehicles. And what are the existing issues in these batteries? Okay, and main issue is safety. Different issues are there, but main issue is safety. That place we are using maximum liquid electrolytes. Okay, in case of liquid electrolytes, there is a lot of problems. I have given here in red color. The issues are mainly flammability, sensitivity to charging, variability, liquids leakaging, sensitivity to deformations. Those are the main issue. And the second one more issue is high cost, and the temperature range is also that we need more. Okay, at present whatever batteries are using, that is in between -20 to 55 degrees centigrade, but we need more broad range. Okay, more broader operating temperature, we should go for that one. Okay, and different other problems in that low energy density and low power density. These are different existing issues in the present batteries. Okay, these are the different accidents happen due to leakage of electrolyte in the batteries in different situations I have given here. Yeah, how can we rectify that one? What is the main problem? Whatever battery we are taking, whenever we are taking about battery, the battery having mainly three parts, mainly anode, cathode, and electrolyte. And what are the properties we have to check for those batteries? Mainly mechanical, electrochemical, and thermal. These are the main properties we have to check. Yeah. And what is the solution for that leakage safety of that batteries? What is the main solution? Okay, the main solution is we have to replace those liquid electrolytes by solid polymer electrolytes. That means polymer electrolyte we are going to replace. That polymer electrolytes we are having four types. Solid polymer electrolyte and a liquid electrolyte also I have given here. Gel polymer electrolyte and inorganic solid electrolyte. Polymer electrolytes are four types. I have given these four. Out of all these four, I have chosen solid polymer electrolyte is the solution for the present existing issues. And if we use the liquid electrolyte, advantages are there and disadvantages are also there. If we use the liquid electrolyte, conductivity is very good, no doubt at all. Okay, and electrochemical performance also is very good. But what about the problems? Okay, the problems are short circuits, internal short circuit problem is there, leakage is there, corrosive reactions, combustion reactions. These are the problems with the liquid electrolyte. Then what is the alternative for that liquid electrolyte? Solid polymer electrolyte. That is the alternative for liquid electrolyte. And what are the polymer we have to choose? Okay, out of all polymers, which is the best one? Okay, based on that, I have chosen PEO. That means polyethylene oxide. Okay, these are the advantages of PEO. These are the advantages of PEO, that is having more amorphous and low glass transition temperature. Those are polyethers. Those are good candidates for as a host material. Okay, these are some of the advantages of PEO. And what are the advantages of solid polymer electrolytes? I have given here: safer, thermally stable, light in weight, easy handling, flexible, and wider electrochemical stability. And what are the minimum requirements for that solid polymer electrolytes? Actually, there is some problems with the solid polymer electrolytes also. Main problem is conductivity. Okay, for minimum requirement of that one is 10 to the power of -4 order. But with the solid polymer electrolytes, it's a bit difficult to reach that conductivity. Around -10 to the power of -6 is okay, but 10 to the power of -4 is difficult to reach. But how can we achieve that one? Okay. And how can we achieve that one? These are the different methods to achieve the conductivity of the polymer electrolytes. We can increase the conductivity by using different methods. Out of these methods, I have chosen nanoparticles incorporation and some ionic liquids also I have incorporated. Here, these are the applications of polymer electrolytes. We can use polymer electrolytes in all these applications, up to lithium-ion batteries to all electrochromic windows. All these applications we have. And literature review, I am not going to focus on this much. This is the this graph represents all the materials conductivity values with respect to temperature, from glass electrolytes to polymer electrolytes. They have given here. And why I have chosen PEO? Because that is a very good material. Already I have given the advantage of that PEO previously. And the salt, what is the lithium salt I have chosen for? Okay, first I have chosen the lithium difluorooxalato borate, LiDFOP. This is one of the new salt. Okay, why we have to choose this one? Actually, LiBF4 and LiBOB, these are the old salts. Already many papers available on those two salts. But whatever salt newly developed, that is LiDFOB, that is the advantage of those two salts. Whatever advantage having LiBF4 and LiBOB, both advantages having this LiDFOB. Okay, that's why I have chosen LiDFOB. The first point I have given here. This salt possesses the combined advantages of LiBOB and LiBF4. Compared with LiBOB and LiDFOB has a higher solubility in carbonate solvents. Okay, these are some of the advantages, and we have published that paper also. Yeah, and another one, this is very, very new salt, LiTDI. Okay, very few papers available, particularly in case of polymer electrolytes. This was first reported in 2004. Okay, and a lot of advantages of these salts compared with the other salts. The remaining other lithium salts are very difficult to handle in open atmosphere, but this we can. Okay, this is not that much reactivity with open atmosphere. And next I have chosen liquid electrolytes and ionic liquids. Sorry, next I have chosen ionic liquids. Okay, these are the very good, we can say, plasticizer also. Okay, but compared to the plasticizer, this is a bit different. Here in this ionic liquids, we are having anion and cation both. Okay, but this will improve the ionic conductivity of the polymer electrolytes very high. But what is the drawback with that? That also we will check. Okay, these are the different ionic liquids I have given here with the different cations and different anions. Yeah, what are the advantages of these ionic liquids? I have given complete picture here. Okay, plasticizing effect, non-volatile, non-flammable. Okay, all advantages I have given here in this. Yeah, this is one paper we have published in Journal of Hydrogen Energy, and this is the effect of this ionic liquid on the LiDFOB system. Okay, and this is the synthesis method of that polymer electrolyte. Okay, and whatever conductivity we have achieved here, that is 10 to the power of -4 order. Actually, whenever we have to use this polymer electrolyte in practical applications of battery, 10 to the power of -4 is minimum. Okay, for that here we whatever electrolyte we have synthesized here, and we have tested with electrical conductivity also. This ionic conductivity, and the ionic conductivity at room temperature, that means 30 degrees centigrade, the conductivity is 1.85 10 to the power of -4 order. Okay, that is very good. And we have compared same system with the another polymer electrolyte. Okay, with LiTFSI. Okay, with LiTFSI, compared with that LiTFSI, this electrolyte having the more conductivity and more electrochemical performance also, and thermal properties also very good compared with the other electrolytes. And I have compared the electrochemical properties. Yeah, check, this is the battery testing, electrochemical properties, and the specific capacity is also very good compared with the LiTFSI polymer electrolyte. Okay, here you can check this one. This is already some other people published this one. The specific capacity is around 110 like this, and you can observe my sample. The specific capacity is around 150. Okay, the specific capacity is also very good compared with the other other batteries. Yeah, and this is also specific capacity. I have performed up to 50 cycles. Up to 50 cycles, the stability is good. And the different ionic liquids and SN, plasticizer, TiO2, nanoparticle, I have tested with the different materials. Ionic liquid, plasticizer, TiO2. Okay, with all the 3 papers also I have published in different journals. Yeah, this is a synthesis of all the material. And the conductivities also I have given here. With ionic liquid, the maximum conductivity I have achieved up to 10 to the -5 order. This is at 10 to the minus 10 this is at 23 degrees centigrade. Remember, actually the conductivity I have shown here, that is at 23 degrees centigrade. With ionic liquid, that is 10 to the -5. With succinylnitrile, that is also 10 to the -5 order. And with nanoparticle, TiO2 nanoparticles, the conductivity up to 10 to the -5 order. Okay, the conductivity is very good. And I have checked mechanical property also. After adding this TiO2 nanoparticles, the mechanical properties also increases. We can observe this stress strain graph. Yeah, and based on those observations, okay, we have concluded that we are trying to increase the ionic conductivity, mechanical properties decreases. We are trying to increase the mechanical properties, ionic conductivity decreases. But we have to balance both. How can we balance that one? For that, we have chosen one new nanoparticle that we can call PAS. That PAS means polyhedral oligomeric silicic resin. Polyhedral oligomeric silicic resin. That is the organic inorganic hybrid nanoparticle. Organic inorganic hybrid nanoparticle. Okay, in that PAS, organic portion that will increase the conductivity, inorganic portion that will increase the mechanical property. By using this PAS based nanomaterials, we can increase the both conductivity and mechanical properties simultaneously. Here I have chosen different PAS polymers, PAS lithium salt, PAS ionic liquids. All these PAS based polymers, lithium salts and ionic liquids, all we have synthesized in our lab in Korea. Yeah, these are the different applications and properties of PAS based material. Okay, actually inside we are having the inorganic case and outside we are having the organic functional groups. Then if we add that PAS based material to any polymer electrolyte, that will improve the conductivity at the same time mechanical properties simultaneously. But previous results that in previous results, if we are trying to increase the conductivity, the mechanical property is decreasing. We are trying to increase the mechanical property, the conductivity is decreasing. But with PAS, we can increase the both. Yeah, these are the structure of the PAS. Inside we are having the inorganic case, SA bonds, and outside we are having the organic functional groups. Okay, this is the nanoparticle, organic and organic hybrid nanoparticle. Okay, yeah. These are different PAS. We are having different PAS materials. See, actually this is PAS PEG. Actually generally we can use as a polymer host PU or PEGs, but here we have synthesized polymer, that is PAS PEG polymers. Okay, this is acting as a host. This PAS PEG polymers we have synthesized in our lab. This in this PAS PEG, okay, inside we are having the inorganic case that will improve the mechanical property. Outside we are having the organic PEGs, okay, that will improve the conductivity. Yeah, these different types of PAS PEGs we have synthesized in our lab. With PEG4, PEG13, PEG44, and we have checked the glass transition temperatures also. That is also very less compared with the pure PU. I have given the TG values of different PAS PEGs. These are the different PAS based polymers. This PAS PEG means different PAS based polymers. Yeah, this is the graph between the crystallinity and glass transition temperature with PAS PEGs, different PAS PEGs. Yeah, this effect of PAS PEG on PU, LiTFSA polymer electrolyte. Yeah, I have checked with all the 3 PAS PEGs. Here the conductivity increasing well, but compared with all the 3 PAS PEGs, PAS PEG4 having more conductivity compared with the other PAS PEGs. Yeah, I have given the conductivity values also. Here, if we added the PAS PEG4, the conductivity almost equal to 10 to the power of -4. This is at -23 degrees. So this is at 23 degrees centigrade. If we go for 30 degrees, the value is almost equal to 10 to the power of -4 order. Okay, and this is the mechanical property of different PAS PEGs, and PAS PEG44 having the very good mechanical property. Yeah, these are the results with different polymer electrolytes with LiDFOB, LiTD, LiTFSA. After adding PAS PEG4, how the conductivity increasing we can observe here. The conductivity increasing well. Maximum conductivity we observed for LiTFSI and LiDFOB. Both are good. Yeah, these are the thermal properties, and the glass transition temperature also is decreasing well after adding this PAS PEGs. And this is the complete data of that one. Yeah, this is the battery performance. Actually, here the battery performance is also very good after adding PAS PEG, and we have tested up to 50 cycles. Up to 50 cycles, that is very good. Okay, this is cyclic voltammetric graph. This is also very good. Oxidation reduction reactions also good here. And here we can check the specific capacity. That is also good. That is more than 160 here. That is very, very good. And different C rates we have checked here. Okay. And we have compared our polymer electrolytes with another system that was published by Zhang et al. Okay. They got the conductivity around 10 to the power of minus 4 order, one type of polymer electrolyte, and another one is 10 to the power of minus 5 order at 25 degrees centigrade. And almost our values, almost comparable with these values.
Please, please conclude.
Yeah, sure.
Please.
Yeah, sure. Yeah, 2 minutes, sir. Yeah, these are the different graphs of their system. Okay. And I'm going to focus. I'm going to explain about the pass-based ionic liquids. And here I have given different pass-based ionic liquids. Okay, those are also having very good conductivity. If we add those to polymer electrolyte, if we are going to add this pass ionic liquids to polymer electrolytes, that will give very good conductivity, no doubt at all. Okay, and last one, pass lithium salt. Actually, this pass lithium salt we have synthesized in our lab. After adding this pass lithium salt, okay, the conductivities are very good. I will show that one. The conductivities of that one is very good. It's almost 10 to the power of minus 4 order without adding any plasticizer, without adding any ionic liquid. The conductivity is very good with the pass lithium salt. Okay, and this is the thermal stability of the graphs. And what is the conclusions are? If we use the pass-based nanocomposites, that will increase the ionic conductivity, mechanical strength, reduces TG and crystallinity, improves the electrochemical stability window. That enhances the electrochemical properties of lithium-ion batteries and lithium air batteries also. That is a good choice for future lithium-ion batteries. And I am very thankful to my postdoc supervisor and PhD supervisor, Professor Hiuri and Dr. Ranveer Kumar. And I am also thankful to my host college, MREC. And these are some of the funding agencies. Thank you all.
Thank you, Dr. Reddy,
Yeah, thank
for
you.
delivering a very nice lectures and sharing your research findings related to the rechargeable lithium-ion batteries.
Yeah.
Thanks to all distinguished speakers of this technical session first. Now I invite Dr. Nikhil Kumar Shukla, co-chairman of this technical session, for formal vote of thanks. Dr. Shukla.
Thank you, Professor Yadav, sir. On behalf of the organizing committee of International Conference on Futuristic Material, ICFM-20, and on my own behalf, I extend my sincere thanks to all the distinguished speakers for making this session, first day of this inaugural session, the technical session, first day, a grand success, particularly to Professor Pandey for sparing his valuable time, Dr. V.K. Tiwari, and Dr. Rohit Shahi, Dr. Reddy. I am hopeful and I am confident that all the participants must be benefited with all these excellent and nice presentation. And on my own behalf, and once again on the behalf of the organizing committee, I extend my sincere thanks to all the participants and particularly to the distinguished speakers. Thank you.
Thank you, sir. Thank you. I thank Professor Lallan Yadav, sir, for sharing this session, and Dr. Nikhil Kumar Shukla, sir, for co-chairing this particular session. I also thank to all speakers, especially Professor Pandey, sir, from Japan, and other eminent speakers. Let me tell you that next session will start from 11 a.m. onwards on 19th of December. The link will be same. I want to welcome you all.